find your sheet that says Acid and Bases Intro. These notes cover a lot of terrain, and so hopefully things will make sense. Some will be review, some will be new. So Arrhenius definition, it says any compound that produces H plus hydrogen ions in solution is an acid. And these are all examples of acids that you've encountered before: hydrochloric, sulfuric, and acetic acid or ethanoic acid. In this case, you have to remember COOH is a carboxylic acid from organic, and it's that H that wants to pop off. So here we're showing the traditional way from grade 10 and 11 how we'd show these reactions. So boom, boom, splitting up, and away we go. A base is any compound that produces OH minus or hydroxide ion in solution. So if you have a metal with OH at the back end, then you have your base. So sodium hydroxide splits up like so, calcium hydroxide splits up like so. But there's a more modern and in many ways more useful definition of acids and bases. So instead of thinking of them as just generating H plus or OH minus in solution, the Bronsted-Lowry definition says an acid is a proton donor and a base is a proton acceptor. And so what we're going to have in a reaction is a proton transferred from an acid to a base. Proton just stands for H plus. And that's because if you get down to hydrogen, that's a hydrogen ion with a +1 charge, well, there's one proton and it would have no electrons. So that all that exists there is a proton. So in this case, HCl is a proton donor because it donated its H to the water, and the water became H0 plus, and then we had Cl minus. A base is a proton acceptor, so in this case, the NH3 accepts a proton, accepts an H, and becomes NH4 plus. So what you see is the HCl compared to the Cl minus, they differ by one hydrogen, and the charge has gone down by -1. When we look at this base, differs by one hydrogen from the NH4 plus, and the charge has gone up by 1. So in all these reactions we're looking at here we have a conjugate acid, this conjugate base, and water is the conjugate base to this thing called the hydronium ion, the conjugate acid. So those are pairs. And you always end up with an acid base on one side and an acid and a base on the other side. Similarly, NH3 is the conjugate of NH4 plus, H2O conjugate of OH minus, and here we have a base, here we have an acid, here we have an acid, here we have a base. So, experimentally, we don't run into H plus. H plus loves to attach itself to at least one water molecule. And so if you take H2O and you stick an H plus on it, you end up with H3O plus. So get very used to this. And this is the hydronium ion. And that's what we're showing here. So some people like to call it a protonated water molecule, meaning the proton got stuffed on the water. And some people like to call it a hydrated proton, that we had this proton and we hit it with water. Conjugate acid, conjugate base pairs. So cleverly we use these acronyms CA and CB to shorthand them. And as I was saying, they differ by a proton. So NH3 is the conjugate base to NH4 plus, and H2O is the conjugate acid to OH minus acting as conjugate base. And it reminds you that each side will have a base and an acid, base and an acid. The K chart is going to tell us about the strength of each acid, and that will also allow us to predict reactions. So stronger acid, as we come down, it's higher up on the left, and if we're looking for a stronger base, it's lower on the right, and you have a K chart in your textbook and the K chart that I've put in your package. So here we have a question. It says H2S, F minus, HF, HS minus. And what we see is H2S is the conjugate of HS minus, so that's why it says conjugate acid here, conjugate base there. It will transfer a proton to the F minus, and the F minus becomes HF, so it's a conjugate acid to F minus. Well, in the first case, we see this has no proton, so this had to be the acid. And this had to be the base, and similarly, this had to be the acid, this had to be the base. Now we go to our Ka chart, and we look up H2S, and it says 9.1 times 10 to the minus 8. And HF says 3.5 times 10 to the minus 4. Well, this number, this Ka, is bigger than that. And so HF is a better proton donor, or a better pusher, so it pushes the reaction to the left. And therefore, the reactants are favored in this equilibrium. It doesn't go to completion, but we're going to end up with more of the reactants than the products at equilibrium. And the other thing is, once we know where the stronger acid is, we also know where the stronger conjugate base is. They always end up on the same side. Polyprotic. Well, protic means proton. Poly means more than one. And so we can have acids that are polyprotic. So H2SO4 can ditch a proton, become HSO4 minus. It can ditch a proton and become SO4 2 So in other words, it can donate 2 protons. And if it's in the presence of strong base, it will. H3PO4 can lose 1 proton, which can lose a second proton, which can lose a third proton. And in a strong base, it certainly will lose all 3 protons. Polybasic would mean it can absorb more than, or take in, or accept more than 1 proton. Amphiprotic means it can act as an acid or a base. That means it can donate a proton, or it can accept a proton. So we have things like HSO4 minus, H2PO4 minus, and HPO4 2 can act that way. So here's H2PO4 minus acting as an acid. That means it has to donate a proton and drop down to HPO4 2 And since the water accepted a proton, it becomes H3O plus. But H2PO4 minus can also react with water. And in this case, a proton can come from the water. That brings us up to H3PO4. 1 more hydrogen, charge went up by 1. And the H2O drops to OH minus. So we threw a lot at you there, and that's a good set of notes that will help you with some of the early stuff, especially Bronsted-Lowry acids and bases, and you're going to have a couple of simple worksheets with them.